Great, so let's get started. This is a front-end oriented talk on some of the rendering technology that Social Tables uses to deliver high-performance editing experiences. So let's start with Diagram. Diagram is a software product that we sell event planners to help them visualize their events. Diagram's primary job is to help people drag floor elements, tables, chairs, what have you, around pre-drawn space. And Diagram is built on React Redux for sort of a performance state passing experience. Redux is great because you have a single source of truth and unidirectional control flow. Immutable.js helps us keep that contract so that when a React component updates, or rather, we are guaranteed a component update whenever state updates because we're not modifying things in line. It also saves a lot of memory if you're doing any kind of transformation on arrays or lists. And we use Three.js for our rendering layer because it's way easier to grok than raw WebGL calls, and it gives you a nice scene state. But Three.js has a mutable world with a lot of separate things, and we'll get into why that's important in a sec. First, though, for Diagram to be useful, event planners need to be able to trust its output. That means that when I drag a table to position XYZ in my world on screen, I expect that that table will fit in position XYZ in the real world. This means that the underlying floor plans have to be to scale and they have to be architectural quality. Fortunately, we have an onboarding team that draws those. And those are drawn in an internal tool that we call Floorplan Creator. Now, I bring this up because Floorplan Creator is actually a really interesting case study in building CAD tools under the constraints of browser rendering. It's a 2D mesh editor and tracing tool, which means basically people are throwing a background image on and they're drawing a lot of lines over it. If you've ever worked with a 3D mesh editor, it's a lot like that, except less of a simple polygon focus, more of a large enclosure drawing focus with a real focus on spatial accuracy. And it outputs these complex nested polygons, which have some interesting properties that I can get into at the end of the talk. Anyway, we've been working on this tool for a very long time. It's gone through a lot of iteration because the effectiveness of our onboarding team scales directly with how easy it is to use. And to get back to the JavaScript community, we've released the most recent variant as an open source project. You can find it at that URL or NPM repo, which is great because this talk is about fun tidbits from that you might want to steal to build your own tooling. So, patterns we'll be looking at today. Fast immutable to mutable state synchronization, nearest neighbor object picking, and guide snapping. So let's jump in. In case you're not familiar with React, React works in the following way. Actually, we're going to talk about React in the context of a React Redux binding. React is mostly sort of this part of the world. What you do when you are setting up a React app is you define all these components and you tell React DOM, which is their library for going between the actual DOM and the browser, and the virtual DOM components that you create through React to render it. And then you have this component hierarchy, and you feed components props, and they spit out divs, basically. Under React Redux, you have a global Redux store, which passes state down through your component hierarchy to individual components. When you want the user to do something, those components may dispatch actions as a result of event callbacks, which will mutate your Redux store by going through user-defined functions called reducers, which are basically functional programming reducers. This gets interesting when you're doing anything involving a canvas. Why? Because lines on the canvas aren't DOM nodes. That means React DOM can't control them. So you're responsible for writing the code that does all that drawing. And it turns out this can be a huge bottleneck if you don't do it effectively. So we're going to talk about some techniques to do that really fast, 60 times a second. And before we can really get into the case study here, let's talk about how we designed the state for this CAD tool. We built FPC with sort of one scene, which contains a big map from ID to data of all of the entities. This includes points, boundaries, objects. And these things have interdependency, but they're in this nice flat map, which has some really great properties for synchronization. When we send an action, like adding a boundary, meaning somebody dragged something from point A to point B, the following happens. We dispatch this Redux action. It goes into the store runs reducers. So in this example, you might have this action that's shaped like this. Your reducer function would combine the set of things that exist with the new set of things that are supposed to exist and spit out the set of things that exist with the new things. After that, React gets a hold of them through Redux connect bindings, and you need to sync stuff into your Three.js scene. Well, a naive approach might be to just refresh the entire scene every time. You know, it's going to work really well, and that's really great for early dev. But the problem is you've got this bottleneck. Well, specifically two bottlenecks. So you have the mesh creation bottleneck. It's fairly expensive to convert very simple data into full-fledged Three.js meshes, especially if you're not reusing them. And second, you've got the CPU-GPU bottleneck. CPUs are very fast. They have access to a lot of memory. GPUs are very fast. They have access to a lot of memory. Sending things from the CPU to the GPU is a bottleneck in most applications, and it's even worse in the browser because WebGL has to do a lot of security stuff to make sure that you're not sending anything terrible to somebody's graphics card. So there's a pretty significant performance cost to resending the whole scene. Well, what can we do about that? We can send part of the scene. If we just added one line, then let's just add the line. Seems like a no-brainer, but under the this is the full state of the world being passed around paradigm, it turns out to be an interesting problem to do. And so this is sort of how we solved it. First, for every state update that our viewport component gets, we take a diff of the previous state of the world and the new state of the world. The diffs work a lot like git diffs. We're looking for adds, updates, removes. So we take those deltas, and it's actually really easy to get these deltas, especially with Immutable. So if you're familiar with Immutable.js, they have some great utilities for iterating across everything inside of a map called value seeks. And because of how value seeks work, Immutable is trie-based. If you're familiar with databases, tries are basically like trees, except all of the leaf nodes have links. So if you're crawling across them, you don't have to go up and down the tree. You can just sort of crawl across all the leaves. What this means is that you can do this diff in n log n time, which is pretty fast. You know, n log n, 60 times a second, not a problem. N squared, you're gonna have a bad time for like 1,000 things seen. So we took that, and we take those diffs, and we worked them. Problem two, you move a point, but you've got things connected to the point. You need a way of saying, if I move the endpoints of a line, I need to redraw the line. Well, that turns out to be pretty trivial too. All you have to do is really understand your dependencies within any kind of a scene and write some code which scrolls across the things that might be depended on and adds anything that changed to the update set. Problem solved. And if you do this, it's very, very, very easy to figure out how you need to mutate your Three.js scene. We won't go into mesh creation here because it's pretty straightforward. But if you use this technique, you can get really good partial update performance out of Three.js. The same pattern also works for updating materials. So let's say we select something and we want it to turn blue because selected things are blue. And we need to change all the materials. Well, we can take a diff of the selection set, whether we've got an array of IDs or a set of IDs or what have you. This also works for updating the collision checker, which we are about to dive into next. Now, object picking and collision detection is kind of an interesting topic for a couple reasons. One, it needs to update whenever the rendered state of the world updates so that you can always interact with whatever's in front of you. And two, because the game industry has been doing it for 30 years already, and it's sort of a whole grab bag of interesting techniques to steal. And so here are the ones we stole. We designed our system around having single entity selection, meaning I click a wall, bulk entity selection, I drag a box, lots of walls, entity snapping. I drag something to a wall, it connects to the wall, it's forever attached to the wall. The challenges are lines are really thin. There are not a lot of pixels. So if you're doing a raw sort of single pixel lookup on where the user's clicking, they're going to have this picking problem where they're hunting and pecking at this line and they can't click on it because the exact spatial position of the cursor just doesn't match up. And second, high precision checks are expensive to run on your whole scene. If you've ever done any kind of collision testing logic, you know that it involves a lot of decomposing things into convex polygons and checking other convex polygons or points in space against them. Fortunately, we can do better. We can use what's called a hybrid collision detection system. You have a broad phase, which is a low accuracy spatial index that's cheap to update, and a narrow phase, which is where you do all the really fun math. And so that's pretty much what we did. For the broad phase, we chose Quadtrees. Now, if you've taken computer science, you probably learned about Quadtrees, but in a nutshell, they give you order n log n, lookup, insertion, and removal, and there's no balancing phase. All they are a subdivision of space. So if you imagine that over here is the center of our tree, and we care about stuff over here and over here. If I'm inserting a node, I might say, is this position in one of the 4 quadrants in this tree? Well, it might be. If there's anything else in the quadrant, we subdivide the quadrant and recurse. And as long as that's bounded, what you get is very, very efficient, cheap spatial lookup that gives you everything within a given bounding region of space. KD trees are another great way to solve this. There are a lot of good spatial indices out there. And for narrow phase, you can just write bespoke math for all of your entity-entity intersection. Points are easy, distance formula. Point to line is pretty easy. You're taking the dot product between projections on the line, and you also sometimes care about the dot product away from the line so that you can calculate how far you are from that line, as well as where you are along its length, so that you're not past or before any of the endpoints. Concave polygon collision checking is hard, but if you decompose it, and there's a lot of open source code out there to do this, Mapbox released Earcut.js a few years ago, and it's phenomenal for it. The math gets really easy, and there's another lib you can plug it into called StatJS that'll sort of take care of all that for you. So this means that whenever our viewport component updates, we're suddenly synchronizing 2 things. We're synchronizing the collision detection system and the rendering system. And to sort of get that logic out of the component, we have these maintainer classes, which are just responsible for taking the information at the state updated from thing A to thing B, figuring out what all the internal diffs are, and applying them. And when you want to look up what you clicked on, all you have to do is figure out where you clicked in space. Well, you can do that by comparing the bounding box of the DOM element rendering your scene with your camera settings, and then what you clicked on, which you can do inside your collision system. Generally, you're doing a broad face check to say, hey, what's near where I clicked? And then you take all those things and you sort them by how close they were to your cursor. And you can weight that sort too, which is great because if you're clicking on the intersection between a point and a bunch of boundaries going into it, you want to bias towards that point because you expect users are trying to manipulate those endpoints more than those lines if they're clicking near them. There's all sorts of ways you can tweak the algorithm to make things easier. Box select is a pretty trivial extension of that. You're just doing polygon checks or polygon bounding box checks. Let's talk about guide snapping for a second. Now, guide snapping is kind of interesting. It's something we don't think about in CAD tools, but when you use something like PowerPoint, or when you use something like Google Slides, or maybe Blender, you expect to be able to align things to other things. And it turns out this is super easy to write, and it's fun enough to write that I thought it'd be a fun tidbit. So here's the algorithm. Select all the possible guides, pick the best guides. You can do it in order and time. So, creating the guides. For every point, create a guide like this, create a guide like this. For every line, create guides extending from it, and save some metadata about where those guides originate. You can memoize this if a state isn't changing, so that you only have to create the guides once, and you can reuse them as somebody's dragging their cursor around the scene. So it's actually really cheap. Then, you pick the best guides. What you can do is, for each guide, you can look at the cursor's position along the ray extending from it, the distance along a perpendicular ray, which gives you the proximity to the guide. You select the closest guide. Guide 2 is more interesting because what you really care about when you're snapping something is where these 2 endpoints meet. This is really useful if you're trying to do something like build a wall which extends from this wall and matches this square's center. And so that's a little more interesting because you have to calculate all of the possible intersection points, then select the best intersection point. And then you move your object to the intersection point, and you're good to go. So takeaways, you can do a lot of good stuff in CAD tools in O(n) log n time. If you're writing n squared, you're probably doing it wrong. Diff calculation is simple and easy, so consider doing it. We all use Git. We all love Git. Let's all be Git. And finally, the video game industry has been thinking about performantly moving things around and figuring out if they're bumping into each other for several decades now. I know as an industry, we are always reinventing the 90s, but let's borrow from the 90s and build on top of them. So that was sort of a lot. You can find this and a bunch of other cool patterns to steal for your own projects at our open source repo, socialtables/openfpc, and on GitHub, github.com/socialtables/openfpc. So, thank you. I hope this was moderately helpful. Any questions? All right, next talk.
He shows the tool.
Yes, and let's jump into what this thing actually does real quick.
There you go.
So here's why you might want to steal from this, if that was a little too cerebral talk-wise. So what you have is a pretty intuitive to use thing editor. We can do things like select a lot of things, transform them fairly performantly in real time. This seems second nature, but it's actually really fun to implement, especially translating back and forth between an Immutable.js back scene and a Three.js rendered space. So these are all matrix operations. We calculate transformation matrices, which actually take the inverse of what you're doing with your cursor relative to the 3D scene and apply that to the thing you're moving around. You have a lot of subtle behaviors, which are really useful if you're ever building a drawing tool, like thing-to-line snapping. And that's pretty simple for lines that are vertical and horizontal, but let's make this a little more interesting. So we can go over here and sort of take this and drag this over. The doors don't move in real time when you do that, but they do move in real time when you transform stuff. So what that means is that this has to have it has to be entity interdependency aware, which has a lot of fun implications that I didn't think I could fit into the slides. It's also got the ability to create arced boundaries, which is some really, really fun trig math. If you like circles, we've got some circles. So it's got that. Walls have meaningful metadata, like the type of wall they are. There's some fun stuff with how those lines are actually drawn within Three.js. These are not GL drawline calls. These are actually triangle draw calls with a shader which extrudes all lines to the left and right. There's a great Medium post called Drawing Lines is Hard if you're interested in rendering technologies like that. And that is a lot of it. Other than that, you've got thing-to-thing snapping. So if we drag a thing to another thing with snapping on, you can see that we have a bunch of helpful hints, which will help that thing be aligned. And if you drag something along a boundary, you can have continuation along that boundary, which is really important if you're drawing walls because people want their walls to match up. And finally, there are a lot of little tidbits like inline arc control, where you can sort of drag the midpoint along something, and we calculate how the curve should be. There's, again, sort of bulk selection, manipulation, and it's all in Redux, and you've got Immutable, so why would you not have an undo redo feature, which is fairly memory cheap. So this is sort of a fun case study in choosing to build CAD tools in the browser. It's very similar to our diagramming tool. So if you're interested in technology like this and want to play with high-performance interactions with lots and lots of scene entities, consider working at social tables. That's a lot of it. Oh, and it supports real-world scale, too. So we can switch units. Let's go in here. We've actually got spatial measurements that update in real time along every wall. You can select metric, imperial, what have you. These measurements will mutate if you do an arc because, hey, arc distance is a thing. So yeah, lots and lots of fun tidbits that relate to spatial hierarchies and objects that are attached to each other. And you can really get in here and, at the very least, make a lot of like fun sort of in-the-moment little artistic experiences where you're messing around with all the arcs maybe, or you know, just playing with it. CAD tools are fun. Thanks.